I could see it. Okay, so first of all, I would like to thank you all for staying here on a Friday evening. You know, it's like for dinner, the best is kept for the end. So we're gonna go now through the QRMM tutorial, and I have to say that it's a long time since I did it myself, so I might have maybe underestimated the effort. In fact, today I showed you a lot of results and simulations, but you know, while I was clicking through the slides, actually setting up each of them takes a lot of time. So I'm not sure. I think we will just end up, hopefully, doing the spectra. I think there won't be enough time to do the dynamics. So major part of this exercise will be how to actually start the simulation, because starting from the crystal structure that you get from the protein database until you have the full setup, it actually takes quite a while. And this is already by simplifying the steps, okay, because we know how to set it up. So let's start. Before I start, I wanted to say that it might be that not all steps will work for you. So in this case, in my directory on the cluster, you have a folder called tutorial. And so we are going to go through 6 steps. And in this folder tutorial, you have 6 subfolders. They're called 1, 2, 3, 4, 5, 6. And so critical files are in this PDB file highlighted in red. So if you don't manage to do the steps, you can go to this directory and grab the file. And so you will, even if this calculation doesn't work, you will be able to proceed to the next step. Okay, now what I don't know is if you have the PDB file, probably not. Maybe I just also put, okay, you know what, we will start, and maybe I will ask in the meantime Juanjo to share it with everyone. Okay, so the first step of the spectrum simulation part is to prepare the PDB. As I mentioned already in my lecture, the crystal structure is usually not below 1 angstrom resolution, so they are not able to see hydrogens. And therefore, when you first download the structure, we need to add the hydrogens and to prepare it properly. So I would like to ask you to go to the protein database, and then there is this ID 7Z0A. This is the PDB code for bacterial rhodopsin crystal structure. So you can go to the database and then type this code, and you will be able to get the PDB file. This is the first step. Still working? With 10. Can you share this PDB with the students?
Yes.
I send it to you.
I will upload it to the OneDrive link I sent you yesterday. I will upload it.
Sorry?
I'm doing that.
This is Juanjo is doing it.
Once I complete.
Is it working? Ah, okay. Okay.
I don't know if I have permission to copy your phone.
You don't have the permission? No, but you can do it to, you probably have the permission to read because we're in the same group. Okay, so do I need to change the permission? Seems so.
The PDF is uploaded in the.
No, but they cannot access to my directory.
Okay. And they need it only for this or for more things?
For more, for every step I put the files. In
Can you
case,
copy from you to there directly?
yeah.
Try to copy from your. Just to, SC key, star, and you copy to everyone.
Okay, just a second. Okay.
I thought they told me they will be able to do that.
El subdirectorio está arriba, o sea, está, no tenemos permiso, solo con que haga el change mode.
Vale, so just give permission to this folder with th mode.
So how was it? Read and execute. It's 1 and 5.
I don't remember.
So can you, does it work now? It's working? Okay. Okay, so the first step in the preparation is that you load Ember tools, and this is done by module load Ember minus tools 19. Okay, and then in this Ember tools, one of the tools is called PDB for Ember. And then you type this command line. So you have the PDB file minus reduce, and then you redirect it into the PDB code underscore reduce.pdb. And in this tutorial, you see this PDB file is red. So in the directory tutorial subdirectory 1, you'll have this PDB already if it doesn't work for you. So this tool in Ember is adding hydrogens to the crystal structure. So we are basically doing this step here, going from the heavy atom structure to the protonated one. So if someone succeeds with this step, please let me know, because I didn't manage to do it here on the class. I did it on our own cluster. There is apparently some mismatch in Python versions. You cannot do it. Okay, so then just go to the directory and grab this file. Go to my directory tutorial. Okay. Okay. So then
then reduce. So that
okay.
the problem is because the currency.
Okay. Okay, you can try it if you want. No, it should.
No?
It doesn't work. Okay. Okay.
I just got one module. Maybe with the other one.
Okay. So as I mentioned, these rhodopsins, they are membrane embedded proteins. So many times when the crystal structure is solved of a membrane protein, and the structure also contains some lipid molecules. And so they don't bother us, but the problem is that if we're going to do a simulation, this lipids will require special parameters, and this will cause some problems. So that's why for this, at this point, we are going to simply delete all the lipids in the PDB file. So you can either open the PDB file 70A reduce PDB with your favorite editor, VI or Emacs or whatever you use, and then look for this, the line where you have in the column number 4, you have the atom, the number, the type of atom, and it's actually heteroatom, and then the 4th column will have the residue. And this, in this case, there are 3 types of lipids. So OLC, OLA, and LFA. Okay, so you have to delete all the residues that you find with this group. Okay, and there, I think there are few. I think from each of them there are like few in the file. I mean, if you want, you can also do it with SED, stream editor. And you can put D, and then whenever any line that contains these 3 will be deleted, but it's up to you. Sorry? The names. So it is OLC, OLA, LFA.
Oh, yes. Yeah, it's different spelling.
Yes, PDB1 is okay. Now, after deleting the lipids, the next step is to add another keyword there, and this is used to indicate that the protein is terminated. So you need to go to the last residue of the protein or to the first occurrence of the water. The water you can find by HOH. So the first time this occurs in the PDB file, you go 1 line above and you put here ter. You put this termination, and this means that the protein finished, and then it will add a terminal residue to the protein. Here you can see the example. This is the water molecule, the first one that occurs, and then this is the third keyword, and then you leave it empty.
What's the difference between atom and gas heteroatom at the beginning of the first column of the PDB file?
I think atom denotes atoms which are part of the amino acid side chain, and the other ones are from those which are not known in the PDB. Okay, so if you have succeeded so far until now, we have the structure of bacteriorhodopsin without lipids, and now it's fully protonated. So while Amber is well familiar with amino acid residues, retinal is not a regular amino acid. So we need to double check if the protonation done by Amber, PDB for Amber was done correctly. So for this, we have to open VMD. So I can show it. New molecule. So you see here, this is the bacteriorhodopsin protonated. You can rotate the structure. And now what we have to do is we want to have a look specifically at the atoms from retinal, if they are correctly protonated. So for this, we click in the VMD main menu on graphics, representations. And then in the selected atom, we select a residue name. And then we put LYR. So the reason why it's called LYR is because if you remember from my lecture, the retinal is linked to the lysine side chain. So now the short name for retinal with lysine is LYR. So we put this res name, and then Amber VMD, sorry, just shows us the retinal together with the lysine. So now we can zoom in. So what you can see here, and I can change the visualization to make it more clear. What you see here that actually the program to protonate the residues made a few mistakes. So one of them I highlighted already in the tutorial. You see that this carbon number 15, which is here, it has 2 protons instead of 1. Because it has a double bond, it should have only 1. And then the carbonyl carbon from the backbone, and also the nitrogen, has no protons. So we need to fix this. And in Amber, there is a tool. If you go to extension, modeling, and then mole factor. This is a tool which allows you to do editing of molecules inside VMD. Do you all have access to VMD or okay? So now I click on this mole factor, and so now it opens a new window, and now it wants to add some molecule to edit. So in mole factor, you go to File, you select New Molecule, and then from Selection. From Selection means is the selection that you would do in VMD representation. Okay, now after loading it, you see all this information that you also have in the PDB. So what we are going to do now is we are going first of all to remove this additional hydrogen. Yes.
Can you explain again from the extension how did you
Did you open already Molfacture?
Yes.
Okay. So then inside Molfacture, just a second.
You want to share the screen because you stop sharing.
Oh. Yes, sorry. Okay. So inside Molfacture, you click new molecule from selection. And then it opens, and then you need to type res name LYR and then start Molfacture. So first of all, I will show you how to delete an atom.
Excuse me.
Yeah.
What is this?
Molfacture allows you to edit the molecule, so we can delete atoms, add atoms, because usually VMD is just for visualization. You cannot change the structure,
Okay.
but with Molfacture you can manipulate.
Okay. Can you continue?
Sure.
After I use the Molfacture, it created one more.
Yeah,
screen,
exactly. Yes.
But it is not showing anything here.
Yeah, but because you need to stay in this window.
Okay.
Hmm.
And you are showing some display about the always.
Yeah, I'm not sure what happened in your case. So let's close it.
You mean the VMD?
No, here. Press here. X. Delete this now. Delete this. Okay, now go. Let's do it again. Modeling. Molfacture. File. Res name.
I'm right.
Yeah, start. Okay, good. Okay. Okay, so now we are choosing in Molfacture, there are several action buttons. First, we want to delete. So I'm choosing delete. But you need to be a little bit careful because sometimes you can delete stuff that you don't want to delete. So be careful with the pointer. So now I'm going to the visualization. And you see this is carbon 15 and it has two hydrogens. So I'm removing one by clicking. So it's gone. Now I go back to Molfacture and I'm going to prepare. And now I want to add the hydrogens. No, I was deleting. First I was deleting. You did it, yeah. Now we're doing adding. So
Which part of the that we deleted? Can you only show again?
yeah, this one.
Nitrogen, okay.
Before the nitrogen. There are two hydrogens and one of them needs to be deleted. So now we're going to add the missing hydrogen atoms. So for this, we are going here in the middle. There's a section called atoms and bonds. And now it's element carbon. So we're changing to hydrogen. So this is the atom we're going to add. And we click on the action button add. So now wherever we are going to click, we'll add a hydrogen. So we have to choose the carbonyl carbon. We can zoom in and then click here. It's going to add one here. And now, okay, I need to go back. I click on select because I want to make the orientation. I want to change the orientation. Okay. So now the orientation is better. I'm going again to add. And now I'm adding here two hydrogens. I click once and then twice. So 2 hydrogens are added.
Nitrogen,
Sorry?
to the nitrogen.
Yeah, to the nitrogen. So, and you can double check if you have done it, you can double check it by going back to the mole factor table. And here you should have now 69 atoms. So if you have 69, you have removed 1 and added 3 hydrogens, hopefully. Okay. So, and now we are going to change the name of 2 of the 2 of the 3 hydrogens. We need to change the name because they're only temporary. Because in the protein, the backbone atoms are connected. They are forming a peptide bond. So we only did it here in order to saturate these bonds, but actually we don't need them, so we will delete them later. So here's a detailed description in the tutorial how to remove it. This is the delete button, this is the add button. Okay, we have added them, and now we need to rename the 2 hydrogens. So one of them we call HDD1. So we can choose, for example, the one added to the backbone carbonyl carbon. I click here and I call it HDD1. And then I go to the bottom, and this is the second one, which is next to the hydrogen, and I call it HDD2. Okay. I hope it worked for everyone. So now, since we made the modification of the retinol, okay, we are going to save it. So we're going to the mole factor window, and then write PSF and PDB files. So this is the option. We want to save this modified retinol. We are going to for later purpose, okay? And I forgot, I mean, sorry, I forgot to say that for some reason there was this H0, so you need to remove the 0. This is the second hydrogen which was on the nitrogen. Okay, so now I'm going to save it, write PSF or PDB files, and so I'm selecting the name retinal.pdb. And here there is some message, you should click no.
Only the selection or the whole file, like the protein and these.
So this will do it only for the retinol. Okay, but in the next step we will do it for the whole thing. So this is until here, and now we are going to go to the mole factor. And now we're going, these changes that were done locally in mole factor on the selected retinol, we are going to transfer these changes to the whole PDB. And this is done by selecting file and apply changes to parent. Okay. So now we have this reduced PDB, but actually the one that we need to edit is the one that we are interested in is called the edited actually. you can see that it has 2 more atoms because we deleted 1 additional and we added 3. So in total, we added 2 atoms. So here you click and then press save coordinates. And it should, and then it's important that select atoms is configured to all. And then you press save. So, and then we call this one BR underscore modified, and the type is already selected by VMD. So this is saved, BR underscore modified. Okay, so this was the first processing of the crystal structure PDB file. And at the end, you should have generated 2 new files. One is called retinal.pdb, and the other one is called br underscore modified.pdb. Both of the files you can get from the tutorial subdirectory 1, if you didn't manage to follow the steps. Okay, now we're moving on to step number 2. The step number 2 is to generate Ember topology. I think yesterday you were running already some simulations of proteins. So in order to run simulations of protein, you need 2 files. One is the coordinate file, which has the actual position. And the other one is the topology. And topology has like the information, what are the atom types, what are the residues, and how they are connected. So this is called topology. So there is an additional file that we need. It's called, I call it delete.mc, and it has the following content. So it has head underscore name and tail name. So this is the first and the last atom. And then it has this information omit name HDD1. This is these 2 atoms are moved out. It has also the charge of it and so on. So what we are going to do now is we will take this retinal PDB file that we created, and we are going to generate parameters for it. Parameters in topology. And these files are called in Ember, they're called FRC mod. So this is a force, no, how it's called, modified force field, I guess, and the prep-in file. And this is generated using another Ember tool, which is called anti-chamber. And so it requires that you load the models. I didn't specify it, but you need to have the Ember tools 19 still loaded. And then you specify here what's the file, the type of the file, it's PDB. What's the name of it? It's retinal PDB. This contains the PDB, and this is the name of it in the PDB file, LYR. And now it's going to generate charges for it and create this FRC mod and the prepping file. So this command, executing this command takes probably a few minutes. Okay, so you can download in the tutorial subdirectory 2, you can download this delete MC file and then use it for yeah, it's actually used in the second step. So for the first step, you can start it and then do the next step later. So there is, I just wanted to say one thing for the cluster, because whenever you are running a command, you're running it on the on the node where you log in. It's called the master node or the login node. And now we are like, I don't know how many, 30 students. So if you're all going to start now anti-chamber, and this takes a few jobs, then the login node and maybe the whole cluster will slow down. So we will see what will happen. But there is another alternative. So we can use the Slurm for this. Usually Slurm is done non-interactively. You write an input file, you submit it, and you wait until it's done. But there is also, for such a short job, you can also run it interactively. So instead of submitting S-batch and the name of the Slurm script file, you can just put srun, and then you need all this, you need all this information like BIOS. I forgot how it's called. Just a second. Okay, now it's not working. Fantastic. So there were in the Slurm script, in the first few lines, there were special keywords for this computer cluster. Let me check just a second.
Minus A, BOC, and so on, minus
Yeah,
A, BOC.
Exactly. So you need to specify. So if you are like adventurous, you can try this srun command, specify this special keyword, and assign, I don't know, 15 minutes, and then you will be able to execute it without interfering with the cluster. So then you will be assigned to a node, and then you can submit it on a node. But okay, maybe if you don't know what I'm talking about, just submit the script, because it might be too. There's also so once you go to a terminal and you send a command, it will be on the command line until it's finished, right? So you won't be able to work in the terminal. So there is a trick. You can press Control-Z at the same time, and it will put it in. It will halt the application. And then you type BG, which means background, and it will put the job in the background, and then you can continue working in the command line. So this preparation of the topology file and the parameters, this is the most advanced and the most tricky part. So it actually, now we're doing it relatively fast, but it really needs a lot of preparation, and you need to be closely familiar with the system you're studying. Because the thing is, for now, for the purpose of this tutorial, I didn't go much into detail, but in principle, there are always in proteins, there are always titratable residues like aspartic acid, glutamic acid, or histidine. Titratable means that the protonation state can vary. And sometimes it can be, an acid can be protonated, it can be deprotonated. And this you have to check. So either you check, compare it with experiments. For example, there vibrational spectroscopy, it can tell you whether one amino acid is protonated or deprotonated, or you can use servers to predict the pKa value. But in this case, in order to make it more simple, we will skip over it. Okay, so once antechamber is done, it's going to prepare one file which is called lyr.ac. So this file has the important information to create a parameter file, and then we are going to use it as an input in the next line, in the next command. It's called prepgen -i, and then we use this lyr file. And then what it does is this command is assigning atom types and charges in specific EMBA format. And so then the output file is called lyr.prepin. And then we need to specify these two extra commands. So this step is done instantaneously. And again, prepgen is something which is part of EMBA tools. Okay, did anyone manage to finish the antechamber? That's running, okay. Okay, so maybe while anti-chamber is still running, we can already discuss the next step. So after prep-gen, you actually generate the parameter files using the Ember tool parm-check2. And this parm-check2 takes the LYR prep-in file and generates the LYR FRC mod file. This is the file that contains the charges and the force constants. This is the important parameter file. So at the end of these 3 steps, you will have 2 files, one called lyr.prepin and lyrfrcmod. And these files are shown in red, so you can go again to tutorial subdirectory 2, and you will have both files there, just in case if you don't manage to do it. Okay, I maybe because we almost have like one, I think the first hour is has almost passed. And maybe while you're waiting for anti-chamber, maybe you can grab take these 2 files, and we can move on to the next step. Because I think otherwise we won't be able to finish. So in the next step, I recommend that you make a new directory, and then you copy these 2 LYR prepin and LYRFC mod files together with the modified bacteriorhodopsin PDB file. So what we did so far in the preparation, we modified the PDB with the whole protein, and now we have defined charges and topology file for the retinol itself. Why did we have to do it? Well, because all the protein part has well-defined parameters in Ember. All the residues are known to Ember, but retinol is not known. So that's why we had to derive these parameters. And now we provide them for further processing to the Ember tools. And hopefully it will create us a file which we can use for simulation. So with these 3 files, the LYR files and the PDB file of the bacteriorhodopsin, you can now start the processing and generation of the coordinate and topology file for the actual simulation. And for this, you need a script called br.tlib. So tlib is the program in Ember, which is preparing this topology and coordinate files that I mentioned several times. So this file contains following information. It sources these 3 files, and these files have parameters. So this one has the Ember parameters for the lipids. This one has the Ember parameters for the protein, and this is the force field 14 SB. So 14 means this was developed in 2014, and SB it's a special edition where the backbone parameters were modified according to new calculations. And then it also sources the parameters of the water. So we're using the TIP3P water, which is a 3-point model of the water. And then you see in the next two lines, the important call for Amber preparation file. So we're loading now this new definition of the LYR residue, which contains lysine and retinol. And then we subsequently reload the parameters. And now comes the protein part. So we are loading the PDB, which we modified. And then we are defining the box. And now we are saving the PDB file using these parameters. The parameters br.parm7 contains all the parameters required for simulation. And the .rst7 file, this is the restart file, it has the coordinates. And then we just say quit. So all these commands are in the br.tlib file. And in order to execute it, you have to type tlib -f br.tlib. Just keep in mind, this needs to be done in the same directory where you have the PDB file and the two LYR files. So these two files and this PDB file. So this allows you to start the actual simulation because it generates the topology file br.parm7 and the coordinate file br.rst7 in the format that Ember knows how to work with. By the way, someone finished anti-chamber or is still running? Oh, I finished. Great. Wow.
Something about the parser.
Yeah.
And well, in practice, what in the FRC mode, we have like it's GAF basically, no, but we are with the atom types from Amber. Like it's a nice approach to use like everything with the atom types from the same portion from the protein, or you can use like GAF for this part and the other. There's no problem for.
Yeah, I think it depends on the type of simulation. So the problem is that GAF is a general force field.
Yeah, but
Yeah.
the parameters come from GAF. Look, same as it's GAF here, basically everything, you know. So just about the nomenclature, you gain something by using the same of the description of the protein or not?
So in principle, this is something, it's very important. So if you have a new atom type, you need to define all the parameters. But so for now, what we are going to do is we're actually going to run for sampling QMMM. So it's for us right now, this is not very relevant. These atom types are important when you run a long MD and you need to really have parameters. It is important because you want to have a force field which is consistent. Okay, so you want to have, because the interactions in the protein are very, they need to be very well balanced. So you need to actually, if you have a new residue which is not parameterized, you need to use the same protocol to parameterize it as the main protein force field. Yeah. I'm not sure if I answered your question.
No, I understand your point, but
Yeah.
it's okay.
No, I think the thing is
Because when you generate
yeah.
the FRC mode,
Yeah.
you can ask that you use GAF, not Amber. So the file has the atom types of GAF. There's no problem. You know?
Yeah, but it's only for those which are not part of the rest. Like if it sees residue, let's say glycine, it will take all the parameters from the set of glycine parameters. But when it sees retinol, it doesn't know this residue.
Okay.
So that's why it assigns the atom type to GAF. Okay. And the atom type has information like connectivity, what kind of bonds and so on. Yeah. Oh, wow. Okay. Okay, I suggest we start now the simulation, and then while it runs, we can make a break of while it's running for like 10 minutes. Okay, so the first step is to do a minimization, and the thing is that because we have prepared the PDB file, we put protons, but we didn't inspect every single added atom, and we didn't inspect close contacts. So if you would start a simulation right away, MD simulation, then this very close contacts that were generated from protonation or modification of the retinal, they would cause the simulation to explode. Because at the beginning, if you have a close contact, it will create a very high potential energy, and this potential energy will be converted into kinetic energy. So they would move very fast, and this will cause the molecule to break down. So in order to avoid it, before running an actual MD, we are doing an optimization. And here the goal is not to find the minimum. The goal is just to relax bad contacts. Okay? If you remember in mole factor, we added hydrogens, and sometimes we added 2 hydrogens to nitrogen, they were very close. So we don't know if the orientation was good. So we are just going to do a few thousand steps of classical optimization. And then this will relax the atoms, and then we can do MD. So in order to do it, we take from the previous step, the parameter and the coordinate file. This is the .parm7 and .rst file. And then we have the input file for Amber. It's written in the mdin_opt. It's saved in this file, which you can find in subdirectory 3 of the tutorial. And it has this is the control file for the simulation. It says that, okay, we are not doing MD, we are doing an optimization, and the total number of the step is 5,000. And here are specific parameters, how often do we save the coordinates, and what's the cutoff, and so forth. And we are going to do this using QMMM already, because the parameters that we have obtained for retinal, they might not be optimal, and we didn't put enough effort to get charges which are done consistently with the charges from the force field. So that's why we are going to switch to QMMM, where the retinal will be treated using DFTB, and then we kind of avoid this problem. So this specific section at the end, you see is QMMM. It says the level of series DFTB. We use dispersion correction. This is something about charges. Shake is equal. So the charge of the QM region is +1. Spin multiplicity is set for singlet. It's 1. And in the QM mask, we select what's actually going to be the partitioning. So we are selecting the LYR residue. Okay, this is this colon and the name of the residue. And then we say, okay, exclude the backbone atoms, CO, NH, CA, and HA. So this will take everything except the backbone of this residue and treat it as QM region. So now in order to run it, you have to prepare a Slurm script. I don't know, do you have a Slurm script already from a previous? No? Okay. Okay. So I think I have a Slurm script already. So, okay, so in my home directory, you will find a file called ember_opt.slurm. And this file has, this is what you need to submit the job. So it has the sender command. Sender is the program in Ember which runs the optimization of dynamics. You can take it, this Slurm script, and prepare it for submission. So the directory from where you do the submission of the Slurm, it needs to contain the following files: the BR_parm7, this is the topology; BR_RST7, this is the coordinates; and the control file for sender, which is called MDIN_opt. Again, all these files should be available in the subdirectory 3. So there is no need to type, all this control file by hand. So the students don't have the Slurm script from before, from other?
This thing?
No, Slurm script. Slurm.
I think so.
Okay. No, okay, I copied them anyway.
No, but it depends. Like for one of what you lectures we have this Slurm script, but it wasn't. Sorry. But it's really fast.
Okay. So you can double check the Slurm script that I gave you if the command is exactly the command here. I don't. This is the important command that executes sender. No, it's not. Do we need to write in the script that we also to load something else except Ember?
No, I don't
No,
think so.
just Ember.
Yes, Ember.
Okay. Yes, Ember. I guess Megan is familiar with this already.
Thank you. We're using it. And actually, the script is working. So,
Which one?
well, the Slurm script. Oh, it's finished. Got it.
So it crashed.
Oh.
And Dina doesn't know what's happening.
Okay, as long as it's entertaining.
Ah, yeah, you need to call it MDIN_opt. And this is what I was saying.
I think we did call it that.
No, but in the script, the
Script itself. Okay. Like that?
yeah, here you see the file is called this, but in the script you call MDIN. Yeah, MDI_opt. So I think there's in the Slurm script that I provided, I think you need to make, I think I wrote MDIN, but you need to write MDIN_opt. I think there is this one typo. Okay, this optimization will take like between 5 and 10 minutes. I'm not sure. So I suggest that you submit the calculation and we make a short break.
But exactly. Yeah, but it's not this correct because it's a termination. Pero es alguien. No, this one, the one that you made, like, it's not working. That's the thing. That's because you have it from the
Sí, es que. Que me falta sí, es que
Still waiting about personalizing. You know, that's what you want. You guys try to stick with neutral lines. Okay, yeah, we have all because now we are going to but Eddie. No, es que sí lo puedo ver, ¿no? Es que sí me lo puedo porque la placa y lo que pasa es Vale, pues tenemos tres. Vale, pues vale.
No, esto es de la anterior. O sea, del 2. Sí, claro.
No, pero ya voy a estar. Ah. Ayer cuando lo dije no bien. No, dijimos chicos.
So I have a question. Anyone managed to submit the calculation?
No, I think there are some parameters missing.
So those are the ones that have in the folder 3 of optimization. Those are well, this is the structure copied from the tutorial. And I think I'm missing this one for sure.
This is you. Okay, can you just list the tutorial? Let's put ls. No, I mean put the command list. ls. Yeah, the directory. Okay, so just put ls.
Okay.
And then home.
Sorry, are you having problems with the separation script?
Yes,
Or-
you have problem?
No, actually, I think I know how to solve that.
Nice.
So,
Just a second.
but yeah, the thing is, I guess the Amber you're importing is not installing the machines you're using. So basically, we would need to use the exports that you used on Wednesday. If you want, I can write them.
Yeah, it would be great. Yeah, thanks.
So this was my original folder, which I copied from you. Then I copied the other files from previous folder too.
Okay. So you're right, something is missing. So the farm 7 and the restart file.
Restart is here, but then this one is missing, I guess. This. So this restart, I have it, but this I don't.
No, but this is going to be the output file. So you have it.
Okay.
So, but you need to run it. You need to have the coordinates and the parameters. I'm going to copy it in a moment.
Okay. No problem.
Okay.
Because we need to
Yes.
clean the coffee machine.
Okay.
So if you don't want, yeah, if you don't have.
Thank you very much.
Don't worry.
No, I think I have something upstairs.
Do you have something?
Yeah.
Okay.
My jacket and I think also the pen.
Okay.
Yeah, but I think I will manage. Mm.
So we do these 3 things before the sander command and all that stuff. So these are basically the exact same commands that that you did on Wednesday with the classical multi-ordinary thing. So the reason is because I think the Amber version that we were importing is not installing the machines we're using. So
I see.
it should be correct.
Okay, thanks, Gustavo.
Sorry, I didn't know you were.
No. Okay, thanks. No, this was good. Okay, great. So I think now it should work. And I also noticed that two files were missing. I put them now into the directory. So from the second step, you should generate this br parm7 and br restart. So if you didn't manage to run this tlib command, if you didn't manage to execute it, then I'm providing you this br parm7 and br rst now in my home directory in tutorial step 2. So you can get it from there.
No,
So, okay, I'm going to say it one more time to make sure that we're all on the same page. Let's synchronize. Okay, so there is the procedure of 6 steps. We went through step 1, 2, and 3, but it turns out, so for those who didn't manage to do step 2 until the end, there are 2 important files, parameter 7 and restart 7. These files are now in tutorial subdirectory 2. Okay, this is one. Second, as Gustavo wrote down, there was something missing in the Slurm script. So some commands were not there. Sorry about this. So you need to add this 3 lines, right? 3 lines into the Slurm script. Maybe we can just edit and then so everyone. You cannot write in my directory, right? No, I think no. But I will just edit now myself. Amber Opsler. Where should it be in the Slurm script?
La versión que la es un módulo no es instalada en las máquinas que son las entonces la cosa es ya puede pero sí pero igual un problema
Where should these 3 lines be? Before the module load or after?
Actually yeah, sorry, I didn't tell you, comment out the module load. So
Comment it out.
Erase it, get rid of it.
Okay.
Yeah, the module load down there, whatever. So instead of that module load, it would be this to export the source.
Amber home user local 2 Amber 18.
Dice que no existe.
Okay, so I modified the Slurm script in my home directory. You can just get it from there now. Sorry, there is one typo. Don't copy it. User Amber 18. Okay, so now you can copy it from my directory.
No, bueno, lo envías en...
Still not
Okay.
working?
So yeah, there's yet another thing because.
Okay. Maybe you just enter it directly in the script,
Yeah.
and so then people will copy it, huh?
But I think the people who's backwards cannot read.
No, but they just copied the file from my home directory, so
No, it's actually in the submission. So
in the submission.
oh no, but it is. Yeah, you can submit like it's batch minus a instead of having the account stuff here. You can do it on command line. So is batch minus uppercase A, and then the biasing. How do you call that? I don't remember. Biasing serve and minus P biasing and then the script.
No, I think you need to edit it.
Yeah,
Yeah, it's better to write it. You want to write it on the board? Or-
yeah, I will write. See, on the full time. Which I don't know. You were able to run it, right? Then I don't know. The other thing is you could you put it on your home and then could everyone else copy from there? What's your user number?
23.
23. Okay.
Is it possible that the other phone, let's say it's not okay? Because if I go to user, I don't find the local show. I find
No, because you don't have access to this folder. That's yeah. I wanted to say that for sure. So yeah, it's only accessible once you have.
But
something.
what if I try the one that I have access? Maybe it works. Because if I continue, I see local Amber.
Ah, there is Amber missing. There is something missing. There's okay. Can you open it?
Yeah, I know, but maybe.
Maybe it's local.
Just
too,
try
but-
ls instead of UI.
No, but I will try this path instead.
But it exists.
Yeah, right. I am just studying.
Oh, okay. Ah, you put tab. Ah, okay.
Right. Why? Because I haven't done these things for years, so it didn't work back in the day. But I don't know. I mean, you could copy his submission script because his is working. He has submitted.
Let's have a look. Ah, yeah, you have a local too.
And
And how do you know it's working?
it was at least
Nice running.
in the queue.
You can see right now the MD out.
Also crashed.
It's not going.
Okay, so don't worry. I mean, the files from all the steps are in the directory. So I suggest, while you know the experts who are familiar with this cluster will try to figure it out, we just move forward with the tutorial because there are like 3 steps, and then we get to the spectral generation, and hopefully they will solve it by then. So I want to mention we did first prepare the PDB file. In the second step, we generated the topology. And in the third step, we are running the optimization. The optimization was done to remove bad contacts. So now with the optimization, in the very last step, you create a file called br_opt restart 7. So this file has the last geometry from the optimization. It's not converged, but at least the contacts are gone, bad contacts, okay? And now we're going to use this optimized geometry to start the next step. And the next step is from optimization, where we don't have any information about kinetic energy or temperature, we are going now to heat up the structure. And this is done with the following input file. It's also in my home directory in tutorial. You find in step number 4, mdin_heating. So this is the control file. It has 2000 steps with a step of 1 femtosecond. So this simulation generates 2 picosecond trajectory, which takes around 8 to 10 minutes. And it's also QMMM. So we are running now a simulation where we heat up the system and we heat it up to room temperature. And then at the end of this step number 4, we again generate coordinates. The last step is saved. And this last step is called br_heat.restart7. Okay, so now we have done optimization to remove some strange contacts or close approach of atoms. Then we heated up the system. And now we are going to do the actual production run. The actual production run was originally planned for 5 picoseconds, but I don't think we will finish because it takes around 20 minutes. So I would suggest we shorten it to, 100 femtoseconds maybe. So this production run is just a MD simulation. Again, we use QMMM. The input file is called mdin_prod for production. And this is step number 5. So here you see the input file. Again, this is the QMMM section. And this is the line to execute. So in every step, in step number 3, 4, and 5, you need to go to the submission script and modify the command to run Thunder. So once you're done with step number 5, we generate the coordinates from the production run, okay? So these are the steps that take quite a bit of time. I think it will take 20 or 30 minutes. I'm not sure. I don't think we will finish in this. But yeah. But you have the files. I don't know. Juanjo, are they going to have access to the cluster after the workshop?
We can give permission.
Yeah.
Now the answer is no. But we can.
Okay.
The computer center to extend.
So okay, so you can take the files with you and run it on your own cluster, and figure out how to set up the Slurm script.
So, but if somebody is really interested, you can write me an email and I will tell you access our computer if you want to do it.
Okay, so let's assume you have run optimization, heating, and the production run. You generate a trajectory of 5 picoseconds, okay? And now we're going to the most interesting and the most rewarding step. This is the generation of the spectrum. So from the production run, we have the file called br_production.nc. And now we can process. So this has the coordinates for the steps that we saved. I configured the control file in a way that you saved only 5 steps every picosecond. So now we process it with the Ember tool called CPP Trudge. So this is a processing tool for trajectories. We enter here the parameter file, and then the input file is this trajectory from production, and this is the output. So it's going to create now, because this .nc file has 5 steps, it will separate them and create RST71, RST72, 3, 4, and 5. It will generate 5 files. And now for each of the files, we are going to calculate the spectrum. So the idea was, because the heating process starts, the initial velocities for the heating are generated using random numbers, that every one of you will run a trajectory and you will get a slightly different geometry. And then you will calculate the excitation energy and send it to me, and then together from, I don't know, 30 times 5, 150 files, I will generate the spectrum. But I don't think we will get to this point. So I suggest that you, if you're interested, you can go to the tutorial, step number 6, and there is this submit.py file. This file is to make your life easier. So what it does, it takes the Ember coordinates, and then from this point, it generates input file for Orca. So Orca is going to be used to run a QMM excitation energy calculation based on this snapshot. So this file is there. You can have a look what it does. And then, yeah, when you submit this Python script is actually going to use another Slurm script and submit every Orca calculation to the queue. So now I'm not sure if it will work, but at least in the preparation, it looked quite good, quite promising. So then at the end, it will generate files which is called frame.1, frame.2, frame.3 until 5. And then the original idea was that you take a copy command and you copy all of them and you change the name to snapshot dot and then your last name and your initial letter of your first name and you send it to me. But okay, we will probably don't do it now. So okay, so at the end, if you run all the steps successfully, you have the submission script, then you get all this. For every snapshot, you get one stick. And as I mentioned in my talk, for every stick we can cover with a Gaussian, and then we can add all the Gaussians. And this is generated from 100 snapshots. This is the computed absorption spectrum for Magdaléo rhodopsin. So if everything would work, you can actually get this. And you see that it's peaked around 400, let's say 60 nanometers. So for your reference, the experimental value is 568. So we are off by 100 nanometers. So, and this can have several reasons. So one is that we run it as a black box. So we didn't check every step. We didn't plot the root mean square deviation. So we don't know if maybe something went wrong. The other thing is that, according to different environments, titratable residues can have different protonation states. So we now assumed, I don't know if everything is protonated or deprotonated, we just took the default values. And this can have a very strong effect on absorption. And the last option is also that we use Cambis-Relip. So we use TDDFT and a small basis set of double zeta quality. So maybe the electronic structure is not well described. So yeah, so this was just some quick technical tutorial of how to set up the simulation, how to run it. I think due to the technical difficulties with the Slurm script and the fact that it's Friday 7:30, I think we can just wrap up at this point. And you can copy the files, or you can, if you want, you can stay longer and continue. But I think that it's a good point now to finish and to call it a day. So thank you very much for staying until this late point. And if you have questions, please, we can still discuss, or you can still ask me. And you can also contact me by email. Sorry? Yeah, 20 minutes. Yeah, sure. Yes. Sure. Yeah.
What kind of constraint we are imposing to avoid the protein?
Yeah, so okay. I think it's a good point I didn't mention. So we were selecting, I think in the input file, I selected all the amino acids in the radius of 5 angstrom of retinol to be flexible. And the other one, I think they have some constraint to. I have to check the file. I don't remember. So this is another important point. Of course, it's really unrealistic to do it in 2 hours, but ideally, since it's a membrane protein, you would have to embed it in the membrane and simulate in the membrane and so on. So kind of like a shortcut would be to impose that implicitly there is a membrane holding the protein from outside fixed. And this we did by, constraining the outside of it. And inside the binding pocket was allowed to move and to propagate in the dynamics. Yes.
I just submit, I guess it's just the QR part, right?
Yeah, it's a QM part, but the protein is represented as point charges in this. So there is a point charge file which is imported in Orca. This is done automatically by the script. So in fact, okay, this is technically this is quite tricky to do it. So what we are doing is we are running an Orca calculation with a mistake in the input file, and Orca works that it first processes the input file, it generates the point charges, and then it notices, oh, there's an error, it crashes. So this takes a few seconds, and then we generate this point charge file, and then we use the real calculation. So yeah, so it's a little bit of workaround, but if you look inside of this Python script, you will see the commands. Here is here. Yeah.
Or you have some more information on the simulations to put into the.
No, the protein is, you have the retinol and the protein is represented as point charges. But the point charges have different positions according to the snapshot.
But so we want to information. You catch different operations.
Yeah.
During simulation.
Yeah.
One that's describing in the no, it's just one way to send
Information about what?
one part is classical and the other one with high level. And in any case, you are only to put into the you don't need any other information from the simulation.
Yeah, but what would be other information? Yeah, I'm like. Because information is the position. Only information is the position. Then in this Python script, it chooses only. Yeah.
If you're